presentation, I will watch the chat box and will interrupt the presenter at the appropriate time. Otherwise, please feel free to ask your questions following our speaker's presentation. Thank you. All right, we still have folks trickling in, but if you're ready, Mankei, I'll go ahead and introduce you.
Sure.
Okay. So it's my pleasure to introduce today's IQUIS speaker, Professor Mankei Tsang from National University of Singapore. Mankei obtained his undergraduate degrees in physics and electrical engineering from UCLA in 2002, and then earned his PhD in EE under Dimitri Psaltis at Caltech in 2006. He spent a couple of years as a postdoc at MIT working under Seth Lloyd and Jeffrey Shapiro before moving to the University of New Mexico to conduct research under Carlton Caves. In 2011, he began his faculty position at the National University of Singapore, where he is currently an associate professor of ECE and of physics, as well as the principal investigator of the quantum measurement group. And over the past several years, Mankei has authored a highly influential series of papers on quantum-inspired super resolution imaging, and some of which I think he'll tell us about today. And so please help me welcome Mankei Tsang. Take it away.
All right. Thank you for the introduction. Thank you for the invitation. Let me share my screen first. All right. I hope you can see it.
Yes.
I think you need to do this. Okay. So let me start by giving you an executive summary of the talk. It's going to be about the fundamental resolution of incoherent imaging from the perspective of quantum information theory. Through the calculations of the quantum limits to incoherent imaging, we found that there's actually a lot more information in the light that you can collect from the starlight or from the fluorescent particle than previously realized. And these quantum limits are very different from the kind of information you can extract using conventional imaging theory. And they have motivated us to invent or propose measurements that allow you to achieve the quantum limits and significantly improve upon conventional imaging techniques. The obvious applications would be astronomy, looking at stars, and also looking at fluorescent particles in microscopy. There could be many other applications like spectroscopy, but I'm going to focus on imaging, astronomy, and fluorescence microscopy in my talk. Let me start with something simple to give you an idea of the basic physics. And then in part 2, I'll move on to the more complicated scenario of having an infinite number of point sources. I will start with 2-point sources in part 1 of the talk. Actually, I'll start with 1-point source, just to tell you the physics. So if you just have 1-point source and you image the point source using an imaging system, using a telescope or using a microscope, then it's well known that the main factor in determining the resolution of your imaging is the diffraction limit. It's coming from the wave nature of light. On the image plane, you'll see a blur spot. The size of the blurring is proportional to the wavelength divided by the numerical aperture. If you're doing telescopes, then and you're looking at angular resolution, then it's lambda divided by the diameter of the aperture. This is obviously very important in microscopy. If you have telescopes in space, then you also have to deal with the diffraction limit. Even for ground-based telescopes, in recent years, adaptive optics has become so good that they are starting to become limited primarily by diffraction, and it now makes sense to build telescopes that have larger apertures to take advantage of the reduced diffraction limit. But these telescopes are extremely expensive, so you will like to have some techniques that, if you have some techniques that allow you to extract more information from the light, given a certain aperture size, then that would, of course, be very useful. If you just have 1-point source, it is now well known that the diffraction limit is not that bad, it's not that detrimental. You can still find the location of this point source very accurately, and you can still find its brightness, of course. The big problem occurs when you have 2-point sources as recognized by Lord Rayleigh back in the 19th century. If you have 2-point sources now, if they are so close that the blur spots start to overlap in the image plane, then it becomes more difficult to tell whether you have 1 or 2-point sources. It becomes more difficult to estimate the properties of the sources. So the resolution limit really should be defined in terms of 2 or more point sources, and when they are very close, then you start to have a problem. It is well known nowadays that Rayleigh's criterion, well, it's a good rule of thumb, but it's a rough idea in the first place. And if you can measure the exact intensity in the context of classical optics, then you can do a lot of many different things like deconvolution or curve fitting or image processing to retrieve the information that you want. So it's a good rule of thumb, but if you can measure the exact intensity, then there are a lot of things you can do to overcome Rayleigh's criterion, so to speak. That's the problem. It's actually difficult to measure the exact intensity according to classical optics, because especially when you're dealing with astronomy or dealing with fluorescence microscopy, your photon budget is limited. And you are going to get noise, photon shot noise, in your intensity measurements. So instead of observing this exact classical intensity orange curve, you see random arrival of photons, so to speak, and you see noise, and then your problem becomes much more difficult. We are going to assume that the photon shot noise is Poisson. This is an excellent assumption for both astronomy and for fluorescence microscopy. And once you assume that it's Poisson, then there's a very intuitive picture of photon shot noise as the random arrival of photons on your CCD. We can study the photon statistics more carefully in astronomy and also in fluorescence microscopy. But the nice thing is that it turns out that the Poisson model is excellent. There may be bunching in thermal sources or anti-bunching in fluorescence sources, but they turn out to be negligible. We've done calculations including these effects, but again, they turn out to be just not relevant in practice. So we are going to stick to the Poisson model from now on. Okay, so you have noisy data. What do? You do statistics. So let's assume a simple problem of 2-point sources, and the unknown parameter that we want to estimate is the separation between the 2-point sources. So you take the noisy data, and let's say you want to estimate this separation, assuming everything is known for now. Everything else is known for now, and this is the only unknown parameter you want to estimate. You form an estimator, and to quantify the performance of your estimation, you can try to calculate the mean square error. But this is usually something difficult to calculate and also dependent on what estimator you use. So in statistics and also in imaging, a very popular theoretical tool is the Kramer-Rao bound. Okay, so the Kramer-Rao bound, it's a lower limit to the mean square error, so that your error cannot go below this error, this Kramer-Rao bound, assuming certain technical assumptions about the estimators. So the bound is expressed in terms of the inverse of something called the Fisher information. Assuming Poisson noise, the Fisher information has a relatively simple expression in terms of the expected photon number and also in terms of the classical intensity of the light on the image plane. It's a limit to any estimator. So it's a good way of quantifying the performance of your measurement. And also it's a reasonably tight bound, because if you do maximum likelihood, your mean square error can asymptotically approach the Kramer-Rao bound. So it's a very popular tool, very useful tool to characterize the performance of your measurement. Let's do the calculation and see what sort of information you can get from conventional direct imaging. We are going to assume ideal scenarios. So your pixels are infinitesimally small, you have 100% efficiency, you don't have any dark counts. And let's see what the information looks like. You can plot it as a function of the separation, the true separation of the two sources. And you see two regimes for the Fisher information. If the two sources are relatively well separated with respect to the Rayleigh's criterion, you see that the information is flat, and that is to be expected, that when they are well separated, you can just treat them as isolated point sources. What's interesting is that if the two sources get so close that they start to violate Rayleigh's criterion and the two blur spots start to overlap, then you see that the Fisher information starts to drop. And if the true separation happens to be 0, the Fisher information drops to 0. The Kramer-Rao bound is the inverse of the Fisher information, so it blows up to infinity. What these calculations show is that you can still estimate this parameter. The Fisher information is still finite if you violate Rayleigh's criterion, but the more you violate Rayleigh's criterion, the more penalty you will have in the Fisher information. So this is what we call Rayleigh's curse in our papers. So there's a penalty associated with violating Rayleigh's criterion, even though sub-Rayleigh resolution is still possible. Things just get more and more difficult if you violate Rayleigh's criterion. So this is something to be expected, nothing too surprising, and it's a behavior that we know for a long time in optical imaging theory and also in microscopy theory. If you are able to control the emission of these fluorescent particles, then there are ways of making sparse subsets. If you make sparse subsets of these fluorescent particles emit in each image, then you can avoid violating Rayleigh's criterion in each image in these well-known super resolution techniques. And then it's well known, you have sparse subsets of the fluorophores in your images. You can find their locations very accurately. You put all the images back together, you get a super resolution image. This is of course wonderful, but on the other hand, you need fluorescent particles, the fluorescence that you can control. And even if you have them, it's kind of slow, and especially for STAD, you have to use a very strong beam, and that introduces phototoxicity. And obviously, the biggest problem with these techniques is that it doesn't work for stars. You cannot control them, or for passive imaging in general. So we are going to look at the problem from a different perspective. We look at the sources. We assume that we are doing passive imaging, so that the only thing you can do is to modify the measurement in the far field. From the perspective of quantum measurement theory, direct imaging, or measuring the positions of these photons on the image plane, is really just one of the infinitely many possible measurements that you can do. As long as your measurement obeys Born's rule, which has this sort of generalized form, then in principle, that is a measurement that is allowed by quantum mechanics. So there are many different, infinitely many different measurements you can perform on the light. The big question is, what sort of measurement would allow you to extract as much information as you can from the light? In this respect, quantum information theory, quantum estimation theory turns out to be useful. This was proposed by Carl Hellstrom back in the 1960s. He found that there's a quantum version of the Kramer-Rao bound that is independent of any measurement that you can perform on the quantum object, perform on the photons. So regardless of what measurement you make, as long as it obeys Born's rule, then there's a measurement independent lower bound that is a lower bound on the classical Kramer-Rao bound for any measurement. And the quantum version of the Kramer-Rao bound is expressed just in terms of the density operator. You have to solve these somewhat difficult equations to get the quantum Fisher information. But otherwise, once you've calculated it, it's really the ultimate amount of information in photons, independent of any measurement. And there's some theory that says that there exists some measurements out there that allows you to extract that information. So that's nice. It's a nice theory in principle, but of course, in practice, you have to calculate these bounds, and that is really difficult. For incoherent imaging, let's use thermal sources as an example. We know what the density operator for the thermal light is. We've known that since the work by Glauber, but just looking at that quantum state written down by Glauber is really difficult to calculate Hellstrom the quantum Kramer outbound. So we need to do a little bit of simplifications. So what we do in our work is to make an approximation that is very similar to the Poisson approximation that people make in practice. We assume that the average photon number per mole is much smaller than 1. This is a wonderful assumption for natural sources, because ultimately you look at KT divided by h nu. The average photon number for natural sources is actually very small at optical frequencies. Once you make that approximation, the quantum state can be much simplified from the exact thermal state, and you can basically just assume that with high probability, you just get 0 photon per mole, per spectral or temporal mode, and with a small probability, you get 1 photon. We are dealing with incoherent sources here, so the photon turns out to be an incoherent mixture of the possibility that it comes from one of the sources versus the photon coming from the other source. So it's an incoherent mixture, and then we are just going to ignore all the higher order modes. You can do calculations, including all the higher order photon counting, multi-photon coincidence events, but it turns out that the theory is very similar. So we are going to ignore those higher order terms. This is an approximation that is consistent with Poisson photon counting statistics, so we can make a useful comparison with all the classical theory, assuming the Poisson model. So we take this model, and now that the problem becomes much simplified, and we try to calculate the quantum Kramer outbound. Actually, I gave this problem, after setting up the problem and setting up the model, I gave the problem to my postdocs, Ranjith Nair and Xiaoming Lu, because we really didn't expect any sort of surprise. It's just a calculation, and I thought it's going to be boring, and I just gave it to my postdocs. To their credit, they found that the problem is actually even easier than I thought. So within a few days, they were able to do the calculation and show these plots to me. This is the calculation done by Ranjith Nair. So the orange curve is what I showed you earlier, and the blue curve is the quantum Fisher information here. So it turns out to be flat. It's constant. It doesn't decrease if the two sources violate Rayleigh's criterion. It's just constant. And if you look at the Kramer outbound, the gap between the two curves is even more dramatic, and you see a huge gap between the two curves. So I looked at this result at the time, and I couldn't believe it, and I told Ranjith, well, you are either going to win a Nobel Prize or you made a mistake somewhere. So I redo the calculations myself, and I couldn't find any mistake. I got the same result. So after some work, a lot more work, so at the end, what I did was I put myself as the first author of the paper. I still feel bad about it, but at the time it was very exciting. Anyway, so this is the surprise, that if you look at the ultimate amount of information in the photons and estimating the separation, the quantum information turns out to be much higher than the classical information that you can extract from direct imaging. So this is promising, but the important question now is, what sort of measurement allows you to achieve that quantum limit? After all, it's just a quantum limit, and it doesn't really by itself tells you how to achieve it. And then at this stage, we were just doing educated guessing, and we looked at different measurements, we do different calculations, and eventually we found that if you look at the light on the image plane, instead of measuring the positions, instead of putting a CCD there, you sort the photons, sort the light in terms of the Hermite Gaussian, or into the what we call the TEM modes first. And then at the different channels, you count the photon numbers in different modes, or in other words, we do spatial mode demultiplexing. We do spatial mode sorting of the light first, and then do photon counting. And it turns out that the resulting information that you get from this sort of measurement allows you to achieve the exact quantum limit. So that turns out to work for a large class of point spread functions. Originally, we looked at the Gaussian point spread function, but there are other work by other people who found that actually just measuring in the TEM modes allows you to achieve the quantum limit, even for other kinds of point spread function. So that's the second important result that we found in our paper. If you want to do the spatial multimultiplexing, actually this is not a new optical concept. There are already many implementations out there in terms of doing this sort of spatial mode sorting. People do that in optical communications, mainly to put more information in the light. So there's already a lot of research on this sort of device. And there are many different implementations of how to do spatial multimultiplexing. So there are many different ways you can use photonic circuits, interferometers, spatial light modulators to do spatial mode sorting. The promise of this idea is basically that you have sources that are classical. We are not dealing with non-classical sources. We are dealing with classical sources. So they are a lot more robust to decoherence and losses. So your experiments are not that difficult to do. We are proposing a technique that can be implemented basically with linear optics and photon counting in the far field. So you don't need to make nano optics or anything like that. You can just magnify your light and work with the light far field. And we have excellent photodetectors, so that is not a problem. And last but not the least, there are killer applications. Even if you're just focusing on two-point sources, there are a lot of scenarios in astronomy and fluorescence microscopy where resolving two closed sources is useful for many different things.
Okay, we have a question from Paul Quaid in the chat here.
Yes.
So he says there's infinite classes of transfer spatial modes. Is there something special about the Hermite Gaussian modes?
There is, and in the next slide, I'm going to give a more elementary explanation of how the spatial multimultiplexing works, so that hopefully once I've given that explanation, you will see why it works so well. Mm-hmm. Is that okay?
Oh.
Okay, so it's a great question because I'm going to explain it in the next slide. If you think about it in terms of optics, you're dealing with classical sources and linear optics and photon counting. So if I tell you a measurement, there should be a semi-classical description of the whole problem. And indeed there is. So let me try to give you a more elementary explanation of why this measurement works. So let's, for simplicity, assume that we know the centroid of the two sources, so that we align it with the origin of the coordinate system. And let's think of the optical field created by one point source on the image plane. Remember, this is diffraction limited. This optical field is actually spatially coherent if it's created by one point source. This is well known if you go through the Van-Cittert-Zernike theorem and all that. So the optical field created from one point source is actually coherent on the image plane. So we can expand this optical field in terms of the fundamental mode with respect to the origin and the first order mode. So it's just a Taylor series expansion. And the amplitude of the first order mode is just proportional to the displacement. So you can do the same thing for the other optical field created by the other point source. There's a Taylor series expansion again. The amplitude of the first order mode is now minus d/2. But remember, we are dealing with incoherent sources here. So the optical field created by the 2-point sources is actually incoherent with respect to each other. They have random relative phase between for these two optical fields. So if you focus on the first order mode and you measure the energy, or measure the power, or measure the energy in the first order mode, then you are supposed to square the amplitude first before you sum them together. Okay, this is just a basic incoherent sum. So the minus sign really doesn't matter. And you do get a significant energy, or in other words, you do get significant signal in the energy of the first order mode that is proportional to d squared. So that's the first important point. When you're dealing with incoherent sources, you do get significant signal that is proportional to d squared in the first order mode. The second important point concerns the zeroth order mode. Notice that at least in this Taylor series approximation, the fundamental mode is just there. It doesn't depend on the signal. It doesn't depend on the displacement. So if you think about it, it's just background. And if you think about Poisson statistics, the variance of Poisson statistics depends on the mean of the photon number. And if there's a background contribution to your measurement and the background doesn't depend on the signal, if you are able to remove it, filter it, channel it to some other channel, then you can just remove that noise and improve the signal to noise ratio. In other words, you have significant signal in the first order mode, and you are removing, by doing spatial mode demultiplexing, you're removing the background, removing the zeroth order mode. So that improves the signal to noise ratio. So the takeaway message here is that there's a very non-trivial subtle interplay between the incoherence of the sources that allow you to get significant information from the first order mode. There's the coherence that is induced by diffraction so that you can do this sort of Taylor series expansion. And also there's the signal dependent noise, the fact that when you're dealing with photon short noise, the variance depends on the mean photon number. So it's the interplay between all these effects that allow you to achieve a significant improvement in the signal to noise ratio. So in hindsight, this is of course kind of very clever and non-trivial. And that's the nice thing about quantum information theory, that you go through the mathematics, it tells you something that is unexpected, and then in hindsight it turns out there is a clever combination of effects that is and now in hindsight you can discover this sort of fortunate combination of different factors that allows you to improve imaging. So does this help?
Okay, quickly, another question in the chat here.
Yes.
For a given average photon flux from the thermal light sources, how does the probability to obtain a measurement outcome that provides the information that saturates the QCRB behave as the two sources get closer? Is this also constant like the QCRB, or what's the rate?
Yes, so you mean in terms of this measurement, right?
I think
how is it compared to the quantum limit?
Yeah.
So if you calculate the classical Fisher information of this measurement, it turns out to be exactly equal to the quantum Fisher information. So it exactly saturates the quantum Fisher information at all parameter values if you measure all the modes.
Mm-hmm.
And if you go through the explanation, you find that for subdiffraction distance, actually only the first order mode is important. But if you manage to measure also the higher order modes, then you get more Fisher information for larger separation. So in theory, if you measure all the modes, it's exactly saturates the quantum Fisher information, and that is quite robust with respect to what the actual point spread function is.
And one more question just added here from Michael Raymer that you might talk about anyway, but do you need to know the centroid, and do the sources need to be equal brightness for this to work?
Yes, so you do need to know the centroid reasonably well. And if your centroid estimation, because the centroid is quite easy to estimate, you do direct imaging and you find that the centroid doesn't suffer from this sort of Rayleigh's curse. So it's essentially constant for all parameter values. It changes a little bit, but it doesn't have this Rayleigh's curse. So the centroid is relatively easy to estimate. Of course, if you don't estimate the centroid exactly, then it's going to introduce some error. you are going to deviate from this ideal behavior. But hopefully at the end of the talk, I'll talk about how to think about the centroid issue, because there's a more general way of thinking about what the effect of not knowing the centroid exactly is going to do to your problem. And in terms of the equal brightness, yes, in part 2 of the talk, I'm going to talk about generalizing the theory to arbitrary number of sources. Okay, I hope I answered the question.
One more here, just to,
okay.
Do you need to know the exact shape of the blue curve in the slide you just showed?
Do I need to know? In the measurement, no.
Yeah.
And the measurement, well, you do need to know the point spread function reasonably well. You do need to know the centroid reasonably well, but in terms of this performance, basically once you've done the measurement, you just do conventional statistics, maximum likelihood, and that's good enough.
He was talking about the point spread function, he clarifies.
Point spread function, yes. I mean, it turns out that the performance of this sort of measurement is reasonably robust to the point spread function, at least if you're dealing with 2-point sources. I'm going to show you some experimental results from other groups, and then that will give you an idea, hopefully.
Yeah,
okay.
Fine to continue.
Okay, so, all right. So, so as I said, the experiments are not that difficult to do. And in fact, after we posted the result on the archive, before the paper was even published, there have been 3 or 4 experiments that were done already. And now there's a steady stream of experiments coming up that are based on our ideas. The first experiment done by the Toronto's group actually is one of the more convincing experiments. Here, what they do is that they take the image plane light from 2-point sources, or actually the image of 2-point sources. Actually, they didn't make the whole imaging system. They just used 2 Gaussian beams incoherent, and they overlap the Gaussian beams and assume that they are the images of 2 coming from 2 incoherent sources. Anyway, they take the light, they pass the light through a faceplate that introduces a pi phase shift to half of the image plane light, and then couple the light into the single mode fiber. So this is their way of doing spatial mode demultiplexing, measuring just this odd mode. So before the faceplate, if the light, think about the fundamental mode. After the faceplate, it's an odd mode. So it's not coupled into the fiber. But if what is coupled into the fiber is this shape, this odd mode, this funny odd mode. So that after the faceplate, it becomes the fiber mode. That this is the mode that they are measuring using this combination of faceplate and the fiber. So this odd mode is obviously not the ideal odd mode that you get from the Taylor series expansion, but there's still a significant, it still looks similar enough to the odd mode, the ideal odd mode that you should measure. And they also didn't measure the fundamental mode, which is not coupled into the fiber or any higher order modes. Despite that, they managed to demonstrate experimentally a mean square error that is around 5 times the quantum Kramer outbound. So it's reasonably close for a first experiment. And also they managed to demonstrate a mean square error that is around 1/10 or 1/9 of the mean square error that you can achieve with direct imaging. Even if you allow bias estimator for direct imaging, and they worry a lot about what happens if you have bias estimators as well. But at the end of the day, they are able to achieve a significant improvement over direct imaging. So that gives you an idea of how robust this sort of measurement is with respect to the point spread function. So in their experiment, the point spread function is Gaussian, but they measure an odd mode that is not exactly the ideal mode, but they still get a significant improvement over direct imaging. And that really has to do with the fact that there's a huge gap between the ideal scenario and what you can achieve in direct imaging. So even though you are not doing the optimal thing, it still gives you a significant improvement. Okay, so this is a good demonstration of what you can achieve even with a simple setup. If you want to do the spatial mode demultiplexing more properly or more precisely, there are actually a lot of other experimental schemes that allow you to do that. You can do interferometry. In this case, it's a Mach center interferometer. In one arm, they invert the image and then do interference. You can measure an odd mode that way. That turns out to work somewhat well in principle. They did an experiment in this paper, but it's not close to the quantum limit. There's this French company, Chi Labs, that sells spatial mode demultiplexers using a sequence of faceplates. And that also seems to work quite well. If you generalize or borrow the ideas that I've been talking about, instead of applying it to the spatial domain, you can also apply them to the time domain, to pulses, to resolve closely separated pulses or resolve closely separated frequencies. Then there's this nice experiments done by the Paderborn's group, where they use some nonlinear crystal and some frequency generation to do effectively spatial mode selection. Turns out that some frequency generation has the same Hamiltonian as linear optics. So they take advantage of that to do spatial mode selective measurements, or there are many other methods. You can also use photonic lantern. I'm not sure how it works exactly, but they claim that it works. So that's the story about 2-point sources. I guess this is another point, good point to stop before I move on to part 2, if there are more questions. Okay, if not, then I'm going to move on to part 2, which is to look at extended extended sources. After all, if you just have 2-point sources, there are not many parameters that you need to worry about. Of course, you can try to do calculations with, for example, 2 unequal point sources or 3-point sources. And some groups have done that recently, but we'd like to stay ahead of our competition. So we are going to move directly from the case of 2-point sources to the opposite extreme, where you have an basically infinite number of incoherent point sources. So now, instead of having just 2-point sources, we have to describe the object, this distribution of incoherent point sources, using a distribution function or intensity function of the object. So if you have 2-point sources, you have 2 delta functions for this big F function. If you have multiple of them, you have a sum of delta functions. And in general, you can just use this intensity function to describe any number of incoherent sources. We still assume that the light is spatially incoherent at the sources. So according to the well-known theory in statistical optics, the classical intensity on the image plane is just the convolution of the object intensity with the point spread function of the imaging system. And you take the magnitude squared of the coherent point spread function, because the imaging system is incoherent. So this theory is well known. Now, if you want to do statistics, let's say your object intensity depends on some parameters, and assuming Poisson statistics still, then you can calculate what is called the Fisher information matrix, which is a generalization of the Fisher information that I just showed. And then you have to invert this matrix and then look at the elements of the matrix to calculate the Kramer outbound. Now you see that this problem is a lot more difficult than the simple problem of 2-point sources, because I'm assuming infinite number of point sources or an unknown number of point sources. So I have infinitely many scalar parameters that I need to specify this object intensity. Or in other words, your parameter space is infinite dimensional. Now you have an basically infinite dimensional a matrix. You have to calculate it, and then you have to invert the infinite dimensional matrix. So it's a very difficult problem. The good news.
Okay, can I interrupt you and ask my own question?
Please do, yes.
So at some point when you have an extended object that's large enough and bright enough, it starts to become kind of funny to neglect the multi-photon components of the density operator, maybe. But maybe your point earlier still holds that those terms don't matter so much. They don't contribute that much information. So I guess what I'm asking is, in your model, are you still neglecting all the higher multi-photon modes? Yes,
that's a good question. Yes, I'm still neglecting all these higher order multi-photon coincidence events. And I'm still assuming the Poisson statistics, which really comes from ignoring those terms. So the argument for using this model, even with many point sources, is that if you look at the experimental literature of astronomy or fluorescence microscopy, I think even for multiple point sources, people still assume Poisson statistics, and that is consistent with my approximation. So I think the approximation is still accurate, because after all, the probability of having multi-photon coincidence is still very low. It's like 10 to the minus 10 usually, lower than the probability you get one photon. So, but it's a good question. I think if your light is in a thermal state, then at the end of the day, the Poisson model, even if the noise statistics is different from the Poisson model, you do calculations using the exact thermal model, for example, then you still get pretty much the same result. So it's just, I don't think it affects the results ultimately. Of course, there are a lot of papers in the literature about using multi-photon coincidence events to improve the resolution. I'm kind of skeptical about whether you do get a good signal to noise ratio, but I really haven't studied this problem enough.
Okay, thank you.
Okay. Anyway, so we have infinite number of parameters, but the good news for us theorists is that it turns out that in classical statistics, people have generalized the theory of Kramer-Outbound Fisher information to deal with precisely this sort of scenario where you have an infinite number of parameters. They call it semi-parametric estimation to deal with basically a parameter space that is infinite dimensional. So for each scalar parameter, you can define the logarithmic derivative of the intensity or the probability density, the same thing. And instead of thinking about this function and do matrix algebra or linear algebra, it turns out to be, if you are dealing with infinitely many parameters, it turns out to be more fruitful, more rigorous, and more convenient to think about everything in terms of Hilbert spaces. Think of the score function, the logarithmic derivative, as an element of a Hilbert space with an inner product that is defined, that is appropriate for statistics. Now you reframe everything in terms of these geometric concepts. For example, instead of thinking about Fisher information, you think about the tangent space of the problem. And instead of thinking about the inverse of the Fisher information matrix, you think about projections of these elements in Hilbert spaces into the tangent space. I suspect that with just this one slide, it's not possible for me to teach you all the theory involved. So you just have to take my words for granted that indeed this sort of theory is useful, not just more rigorous, but also useful in calculating analytically the Kramer-Rao bound. So it's difficult. It involves graduate level mathematics, graduate level statistics, and this book is just hellish to read. But once you understand the concepts, it turns out to be very useful. The results are complicated, so I need to make certain simplifications to show you the rough idea. So I'm going to focus on a regime that we call the sub-diffraction regime, which is sort of a generalization of the sub-Rayleigh regime. Now we have a bunch of point sources, and we think of this distribution of point sources as one composite or extended object. And instead of thinking about the separations, I'm just going to think about the object size. We are going to define the sub-diffraction regime as the regime where the object size, delta, is much smaller than the point spread function width. So this is the analogy or the generalization of the sub-Rayleigh regime for 2-point sources. This is, of course, the worst case scenario in imaging, that if you do direct imaging, what you see is a blur spot, and it's really hard to tell anything about the object. It's the opposite of the good regime that people have been working on for many years, where you have sparse point sources, or you try to force your experiments into this good regime. And there are a lot of nice data processing, like compressive sensing, that you can use to find the locations. So this is the opposite of the good regime. But of course, people have already won Nobel Prizes working in the good regime. So we are going to look at this opposite scenario of the worst case scenario. So all the results I'm going to show you is going to be a function of this object width. So that allows me to simplify the results a little bit. And finally, I want to mention the parameter of interest. Of course, there are infinitely many unknowns in the problem, but in practice, very often there are still very few parameters of interest that you care about in imaging. So I'm going to define the parameter of interest as the moment of this unknown object distribution. So for example, if you're looking at the first moment, then it tells you the position or the centroid of the object. If you look at the second moment, it tells you, for example, it's related to the variance or the object size. So I'm going to define my parameter of interest as the object moment, and then calculate the Kramer-Rao bound. You go through all the theory and make all the approximations I mentioned earlier. And it turns out that you can get an exact analytic solution to the Kramer-Rao bound with respect to this parameter of interest. The easiest way of understanding this Kramer-Rao bound, now that I've redefined everything, the best thing to do is to look at the signal-to-noise ratio, which is the square of the true parameter divided by the Kramer-Rao bound. So the Kramer-Rao bound is sort of a measure of the mean square error, right? So you look at the true parameter itself, take the square and divide it by the Kramer-Rao bound. That is some sort of a signal-to-noise ratio. First of all, it scales with the expected photon number. That's not so surprising. On the other hand, it scales with the object size. So the smaller the object, the more sub-diffraction, the deeper you go in the sub-diffraction regime, the signal-to-noise ratio is going to get worse. And this sort of scaling is worse and worse if you're looking at higher order moments. This is the benchmark that we are going to compare against. This is the Kramer-Rao bound for direct imaging, the conventional imaging method. And we are able to calculate this Kramer-Rao bound. And now we are going to do the same things we did for 2-point sources, calculate the quantum limit, compare it with the Kramer-Rao bound for direct imaging, and see if we get a similar kind of enhancement. So even for direct imaging, this in itself is sort of a new result. in the context of imaging. Now we need to calculate the quantum limit. The bad news is that we need to do the same kind of semi-parametric theory in the quantum regime. The bad news is that this quantum semi-parametric theory was not even invented yet. The good news is that once you read Holevo's book very carefully, you go through the significant difficulty in reading it and understanding it. It turns out that he's proposed all the mathematical concepts you need to generalize the classical theory to the quantum regime. Everything is analogous. And the nice thing about framing things in the Hilbert space is that once you treat things in the Hilbert space, it doesn't really care whether you're looking at quantum problems or classical problems. A Hilbert space is a Hilbert space is a Hilbert space. So you can use exactly the same mathematical tools to deal with the quantum problem once you frame everything in terms of Hilbert space concepts. Anyways, again, I cannot explain the theory in detail. You can read the paper if you want, but it's kind of analogous to the classical theory. So now we try to use the theory to calculate the quantum limit. It's even more difficult than the classical case. We are dealing with a mixed state, so solving these equations is very difficult. We are dealing with a semi-parametric problem, and we are dealing with a density operator that is infinite rank, so to speak, because you have infinite number of spatial modes that are involved. But anyway, with some effort after many years, we managed to prove a quantum bound that is as rigorously as I can. And we calculated this, basically the signal to noise ratio, the quantum limit to the signal to noise ratio. You can compare it with the classical limit for direct imaging. And it turns out that the quantum limit is a significant improvement over the direct imaging signal to noise ratio. If you look at the subdiffraction regime, this is very similar to the case of 2-point sources. And you also get a big improvement if you're looking at subdiffraction regime. And also if you look at the second or higher moments. For the first moment, it turns out that direct imaging is kind of optimal already. If you look at the second or higher moments, there's a significant improvement in the signal to noise ratio. The caveat here, the bad news here is that the signal to noise ratio is still worse if you have smaller objects and if you're trying to estimate higher order moments. Or in other words, I'm not saying that you can achieve arbitrary resolution with the quantum techniques. There's still a harsh quantum limit. And if you have a finite photon number, you still get a limit on the signal to noise ratio, especially for higher order moments, especially for smaller objects. So it's not a miracle, but if you have enough photons and if you're happy with estimating the second or third or relatively low order moments, the quantum bound suggests that there's a significant improvement to be obtained if you can achieve the quantum limit. Let me come back to this elementary picture to explain why spatial mode demultiplexing can help you at least estimating the second movement. So again, for each point source, you have a wave function that looks like this, displaced from the origin. And again, for each point source, you have an optical field that is coherent. You can do Taylor series expansion. And the first order mode has an amplitude that is proportional to the displacement. If you have one point source, the energy is the square of the amplitude, so proportional to x squared. If you have a distribution of spatially incoherent sources, you're supposed to square the amplitude first and then do a sum. The sum, if you look at the expression, it's exactly the second moment of the object. So measuring the first order mode gives you the second moment. So the basic idea is very similar to the case of 2-point sources. But now the second moment plays a similar role to the separation of the 2-point sources. Okay, I think at this stage, everyone would be burnt out by now. So let me go very quickly. If you want to measure the moments, it turns out that the theory becomes a lot more complicated. And just the TEM basis is not enough. It only gives you the even moments. If you want to measure the odd moments, you have to choose a different basis that is derived from the TEM basis. This is assuming Gaussian point spread function. If you have a different point spread function, it's the modes you have to measure in general is a bit more complicated. You have to derive your basis from the point spread function. You can still generalize the TEM theory, the Hermite Gaussian theory, to adapt it for other kinds of point spread function. The theory is similar, but anyway, you need to be more careful about what basis you are measuring the light. Anyway, the key point here is that once you pick the right basis, you look at the mean square error of spatial mode demultiplexing for estimating these moments. It's on the same order of magnitude as the quantum limit, and there's also a big enhancement over direct imaging. This is not just theoretical, but I've performed simulations to confirm that there's indeed a big gap in practice, or in theory and simulations at least. Again, when you're dealing with sub-diffraction objects, and also when you're dealing with second or higher order moments, there's a caveat that I really need to mention, is that the signal to noise ratio at the end of the day is still kind of harsh. It's still worse if you're dealing with smaller objects. It's still worse if you're dealing with higher order moments. So you do need many photons, especially for higher order moments, to compensate for the unfavorable scaling with respect to the object size. Ultimately, if you think about spatial demultiplexing, that has to do with the fact that if you have very small objects, it's just fundamentally inefficient for the light to be coupled into these higher order modes. So the efficiency is low to begin with. So the signal in itself is small. And even though you try your best to measure the right modes, to filter out the irrelevant modes, you reduce the noise, but the signal in itself is just small to begin with. But still, it improves upon direct imaging. So provided that you have enough photons, and you're happy with the lower order moments, then it's still okay. It's still useful, we hope. I think I'm going to skip this. There's a connection between estimating moments and estimating Fourier coefficients if you relate the moments to orthogonal polynomials, but this is still work in progress, I guess. There's a qualitative relation that you can relate the theory that I've been talking about so far to all the super oscillation theory and the literature, but I think I'm going to skip this slide. Anyway, we have been working very hard on generalizing the theory. We have a series of papers generalizing the theory. Most importantly, we have a recent review paper that sort of summarizes all the results, not just by our own group, but by other groups and the experimental progress up until about 2020. So if you need further details, this is probably the first place you can go. I keep a list of all the references that are along this line of research on this website. So if you want to look at the other papers by other groups, you can go to this website. Okay, I think that's all. I'm probably running out of time. Let me give me a minute. I'll come back in a minute. And you can read the conclusion. I'll come back.
Sorry, Mankei, your audio, at least on my end, kind of fell out.
Sorry.
Oh yeah, there you go.
Okay, so give me a minute. I'll come back in a minute, and then I'll let you read the conclusion slide, and then I'll take questions. Thank you.
Okay. That means he's stepping away for a minute for a quick break. maybe if anyone wants to stick around, and I see we have one more question in the chat, so I'll hang out and wait for Mankei to come back.
Okay, I'm back.
Okay, so yeah, there's 2 additional questions in the chat, but maybe it's unnecessary for me to read them now that you're not presenting actively. So can you see them there?
Okay. Is the method somehow equivalent to multi-aperture coherent imaging, such as used in the radio regime to image a black hole? So I guess the right way of thinking about it is that we can potentially apply the theory I've mentioned here to multiple apertures. So, what people do in stellar interferometry. Now you have apertures that is not necessarily Gaussian or any sinc or rectangle or a circular function, but it's some complicated function determined by your multiple apertures. Then the question in stellar interferometry is, how do you design your interferometers, collecting all the light from all the different apertures so that you achieve optimal performance? So the theory I've been mentioning, we focus on image plane, but the thing is, after the aperture, basically you can just assume that everything is lossless in principle. The focusing, the imaging, the magnification, you can in principle model everything using unitary operators. Or in other words, if you calculate the quantum limit on the image plane, it's also valid for any measurement or interferometry measurements that collect the light from the aperture. So the point is that you can apply the same theory to the aperture, to multiple apertures in the problem. We just haven't got the time to do it, but everything I've been mentioning so far is potentially applicable to multiple apertures. And I guess also you mentioned that you mentioned the radio regime. I want to emphasize that the theory doesn't actually, I mean, the theory, you can apply it to radio regime, but the problem there is that the photon short noise is no longer a big determining factor in radio frequencies. You get a lot more photons, you get a lot more thermal noise and technical noise. So all the techniques I've been mentioning, I mean, you can still calculate the quantum limit, but at the end of the day, the techniques are not that useful in the radio regime. There's another question I think earlier about what happens if you don't know the centroid or you don't align your things properly with the centroid. And I think the best way to think about it is to think about the effective object size. This delta parameter that I've defined earlier is actually defined with respect to the origin. So if you misplace your imaging system alignment slightly, then this object size is going to be a bit larger, and it's going to hurt your performance. But as long as you align things relatively well, this delta can still be very small relative to the PSF. So the error in the central estimation or alignment is not that important. So hopefully that answers the earlier question as well. There's a second question. Do you know whether needing to do the model analysis puts harder constraints on the adaptive optics for a telescope application? That is an excellent question, because we do expect that if your adaptive optics is not perfect, then the optimal spatial mode that you need to measure, the opticals that is changing all the time, right? And you're not always measuring the optimal mode. And indeed, things are going to get worse if your adaptive optics is not perfect. But we just really haven't done the analysis to see how much worse or how good your adaptive optics needs to be. I hope that answers the second question. The third question, it seems there's nothing quantum about all of this. The source is thermal, and you can use semi-classical detection theory to calculate the results. Indeed, and yes, once you specify the measurement, then it's classical sources, linear optics, photon counting. You can assume Poisson statistics if you want, and if you want to use a semi-classical model to include bunching or anti-bunching, essentially, then you can also do that. Yes, that's what I mentioned earlier. But exactly, with the quantum theory, what we've shown is the quantum limit. That is the important part about the quantum theory, that you cannot do otherwise with the semi-classical theory. That the quantum theory tells you what is the limit to your estimation, regardless of what sort of measurement that you do. And that limit is applicable not only to linear optics and photon counting, but any sort of measurement. So if you do homodyne or heterodyne or digital holography or multi-photon coincidence events, you do nonlinear optics, you do weak value amplification, any sort of measurement, the quantum limit still holds. So that's the point of the quantum theory. I hope that answers the question.
Yeah, so in that case, we've kept you long enough, and it's very late or very early, I guess, on your side of the world. So please join me in thanking Mankei again for a really excellent talk and generating a really great discussion. Thank you, Mankei.
All right. Thank you. If there are further questions or discussions, I welcome emails. I think that's really the best thing to do when we are on the opposite sides of the earth. So I think emails is the best way to communicate. So feel free to email me if you have any question or any idea. Thank you.
Thanks, Mankei.
Thank you. Let me stop sharing.
Well, it looks like he left. So, all right, I'm gonna sign out then.
Thanks, Mikhail.
Bye.